This diagram compares three storage primitives. If we look at the central model, a traditional hierarchical file system, we see a branching directory tree. Requesting a file traverses that tree, locking index nodes along the path. At scale, millions of simultaneous transactions hit that exact path, creating a severe metadata bottleneck. The hierarchy chokes, while an object storage pool absorbs that identical volume effortlessly. To understand the mechanics behind this throughput, we are going to reverse engineer the architecture of a distributed object storage system capable of holding trillions of objects and serving millions of requests per second. To achieve this scale, the system requires a total separation between the data payload and the metadata that describes it. All hierarchical structures must be flattened into a single addressable namespace. By removing the overhead of physical disk hierarchies, the system eliminates the primary locking bottleneck, allowing for a throughput that traditional file systems are physically unable to match at scale. At the API layer, all data payloads enter the system through a primary logical container known as a bucket. Early cloud object stores enforced a single global namespace. If one tenant registered a common bucket name, that specific name became unavailable to every other user on the planet, leading to naming collisions and complex automation workarounds. Modern architectures scope uniqueness to a specific tenant and region. The control plane appends a regional suffix to the bucket name, creating an isolation boundary. Once inside, the metadata service translates the logical key into a physical hexadecimal object ID. Scoping buckets regionally eliminates cross-tenant naming lockouts. It also provides engineering teams with the highly predictable naming conventions required to scale infrastructure as code deployments across multiple geographic environments. When you look inside one of these buckets, you will likely see a standard folder structure. That hierarchy is an optical illusion. A path like logs/2026/May operates as a flat string prefix. The / is merely a visual delimiter. Client interfaces parse it to simulate folders on screen, but it carries zero structural weight in the underlying database. Instead of organizing files into physical folders, the system uses these string prefixes as its core mechanism for horizontal scaling. Incoming requests are grouped by their specific prefixes and routed to entirely different physical metadata shard nodes. Each individual prefix partition operates with a strict hardware ceiling. Currently, a single prefix partition supports exactly 3,500 write requests and 5,500 read requests per second. If a developer dumps millions of objects under one single prefix, treating it like a massive physical directory, they will instantly hit that hardware ceiling, forcing the system to throttle their throughput. By spreading objects out across thousands of unique prefixes, you activate thousands of parallel partitions. The logical object naming conventions you choose directly dictate the physical hardware throughput you receive. With the metadata translated and partitioned, the operation moves downward to the data service, the massive physical infrastructure that manages the raw bytes on disk. To route payloads accurately at this scale, the data service relies on the crush algorithm, controlled replication under scalable hashing. Instead of a centralized lookup table that becomes a bottleneck, the crush algorithm calculates a mathematical hash mapping an object to a placement group ID. This deterministic map routes redundant copies to completely distinct physical failure domains, like independent racks. Once the data reaches its assigned rack, the operation is handed over to the local storage node, which is operated by an internal key-value store known as shard store. Shard store organizes the underlying hard disk into extents, fixed-size, contiguous physical regions of storage. Using a log-structured merge tree, shard store maps the incoming shard ID to specific data blocks, writing them strictly left to right within the extent. Enforcing sequential writes eliminates mechanical overhead, maximizing disk throughput and preventing write amplification. The global data plane scales infinitely. Network replication is handled by crush, while shard store strictly manages local disks. Early distributed storage architectures suffered from a well-known flaw: eventual consistency. If you updated a file and immediately tried to read it, you risked pulling a stale version from a cache that had not yet synced. Solving this required engineering a system that guarantees strong read-after-write consistency, while maintaining a baseline requirement of 99.99% availability. This split screen illustrates the solution. On the right, a client writes data directly through a high-speed cache and into the main metadata store. Crucially, an independent witness service strictly observes and logs this exact mutation. When a client subsequently requests that data, the read operation hits the high-speed cache first. Before returning any data, the cache initiates a verification check. The witness confirms the cache is fresh, and data is served immediately. If the witness flags the cache as stale, the system automatically bypasses the cache entirely and queries the main metadata store directly to ensure the correct version is returned. This precise choreography between the cache, the witness, and the main store bridges the fundamental gap between extreme high-speed performance and absolute data accuracy. We can now view the entire architecture in a single system map, routing from the API gateway down through the metadata databases and the crush algorithm directly into the shard store physical disks. Because the metadata logic is kept strictly separate from the physical data bytes, engineers can manipulate the placements of these components to create specialized network topologies. This schematic shows the standard general-purpose bucket topology, spreading components across 3 distinct availability zones to guarantee 11 nines of durability. Conversely, directory buckets explicitly co-locate both data and metadata within a single availability zone. Shortening the network path drops request latency into single-digit milliseconds, enabling 2 million transactions per second for workloads like AI training. The system achieves these results by strictly enforcing a flat namespace, completely decoupling the metadata, utilizing deterministic algorithms, and backing it with a witness consistency engine. Exabyte cloud scale is ultimately achieved by engineering the complete decoupling of logical metadata from the underlying physical bytes.